Picture this, a young, fiery solar system still in its chaotic infancy, where planets are just beginning to find their place around a newborn sun. Our Earth, a molten sphere of potential, orbits alongside its closest companion, a scarred, battered moon that bears the marks of a cosmic assault unlike anything we can imagine today. Those craters, visible even to the naked eye on a clear night, tell a story of violence and transformation, a story that may hold the key to why life thrives on our planet. Welcome to the mystery of the late heavy bombardment, a cataclysmic event that reshaped our moon and, quite possibly, seeded the ingredients for life on Earth. Join us on an epic journey back 4 billion years to uncover the chaos, the science, and the surprising consequences of this cosmic blitzkrieg, a tale that will leave you awestruck at the forces that shaped our world. Gaze up at the moon on a clear night, and you'll see a celestial canvas marked by craters, some so vast they're visible from hundreds of thousands of miles away. These aren't the gentle brushstrokes of time, but the brutal scars of a cosmic barrage. The moon's surface, pockmarked and weathered, stands as a silent witness to a period of unimaginable violence. Unlike Earth, which hides its ancient wounds beneath shifting tectonic plates and eroding winds, the moon preserves its history in stark relief. Each crater is a testament to a meteorite's impact, a moment when the heavens rained destruction. But what if this wasn't a slow, steady siege? What if instead the moon endured a sudden, apocalyptic storm of impacts in a cosmologically brief window of time? This is the heart of the late heavy bombardment theory, a hypothesis that suggests a surge of meteorites pummeled the moon between 4.1 and 3.8 billion years ago, leaving scars that still whisper secrets of our solar system's turbulent past. When the Apollo astronauts returned from their historic lunar missions, they brought back more than just stories. They carried 382 kilograms of moon rocks, each a geological time capsule. These samples, collected from diverse craters on the moon's near side, revealed a startling pattern. Radiometric dating showed that many of these rocks, melted and reformed by the intense heat of meteorite impacts, dated to a narrow window, roughly 4.1 to 3.8 billion years ago. This wasn't a random scattering of impacts over eons, but a concentrated spike, suggesting something extraordinary happened during this period. The rocks told of a time when the moon was battered relentlessly, its surface liquefied into magma that later cooled into the scarred landscape we see today. This evidence gave rise to the term late heavy bombardment, a name that captures the intensity of this cosmic onslaught. But why did this happen, and how did Earth, so close to the moon, fare during this cataclysm? To understand the late heavy bombardment, we must travel back to the dawn of our solar system, 4.6 billion years ago. Imagine a vast, swirling disk of gas and dust orbiting a proto-sun that's just beginning to ignite. Within this chaotic nursery, particles collide, clump, and grow, forming planetesimals, small bodies that would eventually coalesce into planets. Over a mere 100 million years, this process of accretion sculpted the terrestrial planets we know today: Mercury, Venus, Earth, and Mars. Our moon too was born in violence, likely from a colossal impact that ejected molten material from Earth's surface into orbit, where it cooled and solidified into our celestial companion. By 4.1 billion years ago, the inner solar system had mostly settled, with most loose debris swept up by these growing planets. So why, after this period of relative calm, did a sudden surge of impacts batter the moon? The answer lies with the solar system's heavyweight champion, Jupiter. With more than 2.5 times the mass of all other planets combined, Jupiter's gravitational influence is immense. Scientists now believe that Jupiter didn't always orbit at its current distance of 768 million kilometers from the Sun. In the solar system's early days, it embarked on a dramatic journey. As it formed, Jupiter was dragged inward by the dense gas cloud surrounding the young Sun, spiraling closer to where Mars orbits today. But it didn't travel alone. Saturn, the second gas giant to form, followed a similar path. When their orbits aligned, their combined gravitational pull created a cosmic tug of war that reversed Jupiter's inward march, pulling it back to its current orbit. This grand migration, known as the Grand Tack hypothesis, took place over mere hundreds of thousands to a few million years, but its consequences were profound. Jupiter's journey through the solar system was like a cosmic bulldozer, disrupting everything in its path. The asteroid belt, now home to 1 to 2 million asteroids between Mars and Jupiter, was once far more populous, containing perhaps 100 times more material. As Jupiter swept through, its immense gravity scattered these asteroids, sending them careening through the solar system. Some were flung outward, others inward, toward the inner planets, including Earth and the Moon. This disruption didn't just involve one type of asteroid. S-type asteroids, stony and dry, originated closer to the Sun, composed of silicate materials and nickel iron. C-type asteroids, or chondrites, hailed from the outer solar system, rich in water and organic compounds. Both types were caught in Jupiter's gravitational wake, raining down on the Moon and Earth in a cosmic deluge that would leave lasting marks. While the Moon's scars are still visible, Earth's surface tells a different story. 4 billion years ago, our planet was a hellscape of molten rock, shrouded in a toxic atmosphere of methane and ammonia. Its surface, a thin crust floating on liquid magma, was constantly reshaped by tectonic activity far more intense than today's. As asteroids bombarded Earth, they brought not just destruction, but creation. These impacts delivered vast amounts of water, locked in C-type asteroids, along with metals like lead, nickel, copper, and gold. Unlike the Moon, Earth's dynamic surface erased the craters, recycling them through tectonic churn, but the water and minerals remained, embedding themselves in the cooling crust. Had this bombardment occurred earlier, when Earth's surface was too hot to sustain an atmosphere, this water might have boiled away into space, leaving our planet as barren as Mars. Instead, the timing was perfect, transforming Earth into a water-rich world capable of supporting life. The late heavy bombardment may have done more than reshape Earth's surface. It may have sown the seeds of life itself. Scientists have long puzzled over how life's building blocks, hydrocarbons and complex organic molecules, first appeared on Earth. Remarkably, all 5 nucleobases essential for DNA and RNA have been found in meteorites, suggesting that the cosmos delivered these critical ingredients. During the bombardment, massive asteroids and comets, some carrying water and ice, crashed onto Earth's cooling surface. Unlike modern meteorites, which burn up in our atmosphere, these larger bodies could have survived impact, depositing their molecular cargo into the primordial oceans forming at the time. As the bombardment waned around 3.8 billion years ago, life began to emerge, hinting at a profound connection between this cosmic event and the origins of biology. Why do we know so much about the late heavy bombardment from the Moon, but so little from Earth? The answer lies in their differing geologies. While Earth's surface was a dynamic, recycling crucible, the Moon's was already stable, lacking the tectonic activity or weathering that erases evidence over time. Its craters, formed by those ancient impacts, remain pristine, covered in a fine dust of pulverized rock that has sat undisturbed for billions of years. The Apollo samples, dated to around 3.9 billion years ago, confirmed that these impacts occurred during a narrow window, aligning with the end of Earth's Hadean period. But the Moon's story isn't without controversy. Some scientists argue that the impacts may have been spread over a longer period, a gradual tailing off from the solar system's formation, rather than a sudden spike. Limited samples and evolving dating techniques have fueled this debate, leaving room for future missions to clarify the truth. The quest for answers continues with NASA's Artemis program, which aims to return humans to the Moon as early as 2026. These missions promise to collect new samples from diverse lunar regions, potentially resolving the controversies surrounding the late heavy bombardment. By studying rocks from different craters, scientists hope to confirm whether this cataclysm was a brief, intense event or a prolonged process. Each sample could unlock new insights into the solar system's history, shedding light on the forces that shaped our planet and its satellites. The Moon, with its unblemished record of cosmic impacts, remains our best window into this ancient era, a time when the heavens themselves set the stage for life on Earth. The late heavy bombardment, whether a sudden blitz or a prolonged siege, tells a compelling story of transformation. It explains how Earth, once a molten ball of rock, became a blue oasis teeming with life. The water that fills our oceans, the metals that power our industries, and perhaps even the organic molecules that sparked life, all may owe their presence to this cosmic event. Next time you sip a glass of water or wade into the sea, consider the journey of those molecules, delivered by asteroids billions of years ago in a stroke of cosmic fortune. The late heavy bombardment reminds us that our planet's story is one of resilience and serendipity, a tale written in the stars and etched into the very ground beneath our feet. The role of Jupiter and Saturn in the late heavy bombardment extends beyond their initial migration. Their gravitational interplay didn't just disrupt the asteroid belt, it reshaped the entire architecture of the solar system. As these gas giants danced through the early solar system, their massive gravitational fields acted like cosmic shepherds, herding smaller bodies into new orbits. This dynamic interplay, often referred to as the Nice model, named after the city in France where it was developed, suggests that the gas giants' migrations triggered a cascade of instability. Neptune and Uranus, too, may have shifted orbits during this period, further scattering debris across the solar system. This chaotic reshuffling sent comets and asteroids hurtling toward the inner planets, amplifying the bombardment. The Nice model adds depth to our understanding of the late heavy bombardment, illustrating how the movements of distant giants could ripple inward, leaving scars on the moon and resources on Earth. Beyond water and metals, the asteroids of the late heavy bombardment delivered a chemical bounty that may have been crucial for life. C-type asteroids, rich in carbon and organic compounds, carried molecules like amino acids, the building blocks of proteins. These molecules, found in meteorites today, could have survived the intense impacts of the bombardment, especially in the cooling oceans that were beginning to form. The energy from these impacts may have even catalyzed chemical reactions, creating complex organic molecules in Earth's primordial soup. This idea, known as panspermia, posits that life's ingredients, or even life itself, could have been seeded by extraterrestrial visitors. While the debate over panspermia continues, the late heavy bombardment provides a plausible mechanism for delivering these vital chemicals, setting the stage for the biochemical processes that would eventually give rise to life. The moon's lack of atmosphere and geological activity makes it a unique archive of the solar system's history. Unlike Earth, where wind, water, and tectonics erase the past, the moon's surface is a frozen snapshot of events billions of years old. The craters we see today, like the massive Imbrium Basin, are relics of the late heavy bombardment, their smooth floors formed by lava flows triggered by the heat of impacts. These features tell a story of a solar system still settling into its modern configuration, with leftover debris from planetary formation bombarding the inner planets. By studying the moon, scientists can piece together a timeline of events that Earth's active geology has erased. Future missions, like those planned under Artemis, aim to explore the moon's far side and polar regions, where new samples could reveal whether the bombardment was a singular event or part of a longer, more gradual process. The late heavy bombardment remains a topic of heated debate among scientists. While the Apollo samples suggest a spike in impacts around 3.9 billion years ago, newer studies using advanced dating techniques have raised questions. Some researchers propose that the bombardment was less a distinct event and more a prolonged tail of impacts from the solar system's formation. The limited number of Apollo samples, all from the moon's near side, may have skewed our understanding, as different regions could tell a different story. Additionally, processes like volcanic resurfacing on the moon could have reset the radiometric clocks of some rocks, complicating the timeline. This uncertainty underscores the need for more lunar exploration, as only a broader sample set can confirm or refute the bombardment's intensity and duration. The debate itself is a testament to the scientific process, where questions drive discovery and every answer sparks new inquiries. Earth's ability to withstand the late heavy bombardment and emerge as a habitable world is a story of remarkable resilience. While the moon was scarred, Earth's dynamic geology absorbed and transformed the impacts. Its magnetic field, generated by a molten iron core, protected the atmosphere from being stripped away by solar winds, preserving the water delivered by asteroids. The formation of a stable crust allowed oceans to pool, creating environments where life could take root. This contrasts sharply with Mars, which, despite also receiving water from the bombardment, lost much of its atmosphere due to a weaker magnetic field, leaving it a dry, barren world. Earth's unique combination of size, composition, and timing allowed it to capitalize on the cosmic chaos, turning a barrage of destruction into the foundation for a vibrant, life-filled planet. The story of the late heavy bombardment is a reminder of how interconnected our planet is with the cosmos. Every crater on the moon, every drop of water in our oceans, and every molecule in our DNA ties us to the violent, beautiful chaos of the early solar system. By studying this event, we not only uncover the history of our planet, but also deepen our appreciation for the delicate balance that makes life possible. Platforms like Brilliant make this journey of discovery accessible, offering interactive lessons in astronomy, physics, and data data analysis. With courses designed by experts from top institutions, Brilliant helps you build the skills to explore the universe's mysteries, whether you're a budding scientist or a curious mind. Try it free for 30 days and get 20% off a premium annual subscription by visiting their website. Let's keep exploring the cosmic forces that shaped our world and the universe beyond. While asteroids played a starring role in the late heavy bombardment, comets likely contributed to the cosmic chaos as well. Originating from the distant Kuiper Belt and Oort cloud, comets are icy bodies rich in water, methane, and organic compounds. Jupiter's gravitational influence didn't just scatter asteroids, it also perturbed the orbits of these far-flung comets, sending some hurtling toward the inner solar system. Unlike the rocky S-type and C-type asteroids, comets brought a different chemical signature, with higher concentrations of volatile compounds. Their impacts on Earth and the Moon would have added to the deluge of water and organic material, further enriching the primordial environment. The interplay of comets and asteroids during the bombardment paints a complex picture of a solar system in flux, where diverse bodies from different regions converge to shape the inner planets. Understanding this mix is crucial as it highlights the varied sources that contributed to Earth's habitability, making our planet a unique crucible for life. The late heavy bombardment's influence extends far beyond the ancient past, shaping the world we inhabit today. The metals delivered by those ancient impacts, gold, copper, nickel, and more, formed the backbone of modern industries, from electronics to infrastructure. The water that fills our rivers, lakes, and oceans, sustaining ecosystems and human civilization, owes its presence to those cosmic deliveries. Even the moon, with its iconic craters, serves as a cultural and scientific touchstone, inspiring art, exploration, and discovery. The bombardment's legacy is also a reminder of our planet's place in a dynamic universe, where chance events billions of years ago set the stage for everything we see today. As we stand on this blue planet, gazing at the moon's scarred face, we're reminded that our existence is tied to a cosmic drama, one that continues to unfold as we explore the stars and seek to understand our origins. The late heavy bombardment is more than a scientific theory. It's a saga of cosmic proportions, a tale of destruction and creation that set the stage for life on Earth. From Jupiter's gravitational dance to the moon's scarred surface, every clue points to a universe in constant motion, shaping worlds through chaos and chance. As we continue to explore the moon and beyond, we inch closer to understanding our place in this vast cosmic tapestry. Stay curious, keep exploring, and join us for the next chapter in the incredible history of our beautiful blue planet. The universe has more stories to tell. Will you be there to hear them?